Hey everybody. So as a developer advocate, I get to talk to a lot of teams trying to figure out how to use Hedera. And something I find really useful is to kind of establish a baseline of understanding of what the heck we're talking about. So when I get together with a new team and they want to know about what they can do with Hedera, the first thing I ask them is, what is a DLT? What is a distributed ledger technology? And what's the purpose of it? Is it storage? I mean, if you think about it, there's a lot of companies that are using DLTs as a way of shared storage. But we've got S3, we've got Dropbox, we've got all these tools that do storage really efficiently. As a matter of fact, with DLT, storage is really inefficient. It's 100% replication in the case of Hedera. And if you need that level of storage, great. But it's definitely not the most efficient way to do it. So I would say that storage isn't the reason for a DLT, but maybe trusted storage might be the right reason for DLT. What about compute? Some people say it's about the compute. But when I think of distributed compute, I think of parallel processing, of optimizing the compute to accomplish some very big task like rendering farms. That, to me, is distributed compute. And if you have to compute the same thing on a whole bunch of servers, that's not the most efficient way to do it. But maybe we call that trusted compute. So is DLT about storage? Are we solving a storage problem? Are we solving a compute problem? I'd argue that actually what we're doing is we're solving a trust problem. It's about trust. And that being said, I think there's lots of ways we can get trust. And with Hedera, we can talk a little bit about how you get trust on our platform. And there's a few options. So let's start off with the first option. Option number one is you can ask around. So let's look first at cryptocurrency, right? So we've got 3 services on Hedera. We've got cryptocurrency, we've got file system, we've got smart contracts. But I'm just going to focus on the cryptocurrency side right now because I think it's the most simple of the services, as some of you learned during the hackathon. It's the one I think would be the easiest to illustrate my point of how do we develop trust with a cryptocurrency. So option one is ask around. So when I send a transaction, I'm going to send it to one of the Hedera nodes. And that Hedera node is going to go ahead and pass it around and reach consensus with the rest of the network, with all the other nodes. When that's complete, I can go in and ask for a receipt. And that node is going to come back and tell me that it has reached consensus or hasn't reached consensus yet. But when it has, I get a receipt that says it's reached consensus. And this might be good enough for most of you, especially if you're dealing with micropayments. But what if you don't trust that node? What if you don't want to trust just one node? Well, you could always take your transaction ID and go get receipt from another node. And as long as you do it fast enough, that node should hand you back the exact same receipt. And now we've got a little bit of trust that we've built. Basically, I submitted a transaction, but I don't want to trust just one node. I'm going to go ask multiple nodes, and I'm going to get this receipt. Now this receipt, the reason why we ask multiple nodes is a receipt is a node's perspective of consensus. Every node has their own perspective of a consensus. And you can go in and you can ask each node what your thoughts are on consensus. And you can stop at 2, you can go on to 3, you can just do 1. Maybe you don't even want to ask for a receipt because you're okay with the pre-check. But option 1 to build trust is to use receipts and ask multiple people who have their own perspective, or multiple nodes who have their own perspective. Option 2. We've got something called state proofs. This is a fun one, and I hope everybody gets to learn a little bit about what state proofs are, because I'm going to explain it a little bit. But in a state proof, I'm going to submit my transaction, plus in my transaction, I'm going to ask it to create a record. There is a Boolean in there called record, and I set that Boolean to true. And I say, create a record for me. And that node's going to go around and get consensus with all the other nodes. And then what happens is because I ask for a record, they're all going to create a file on their own file system that represents my transaction. It's going to have a bunch of metadata. It's going to have my original transaction in there. So you're basically taking this transaction that you sent to them, and they're storing it to the file system. And then they're going to collect a bunch of files in a round. There's going to be a lot of these. And then they're going to take those, and they're going to hash the files. So we're going to have the hashes there. And then what we do is we pair up the hashes, and we create a hash of the pairs. And then we take those pairs, and we hash those together. And that gives us what we call a Merkle tree. And that very top hash is what's called a Merkle root, which is a proof of everything that's below it. We can't fake this. We can't reproduce this. And if you see that there is a path in that tree that points to my original file, the white lighter path is the one that points to my file. There's 3 hashes, the root hash, the Merkle root, and the intermediate root, or the intermediate hash, and then the hash of my actual file. So that path is sufficient to prove that this root is connected through hashing to my file and shows that this file is now part of this system or part of this state. And then as a node, what I'm going to do is I am going to sign the root. So I only have to sign 1 hash at the very top of this root as a node. And then I'm going to go around and collect up signatures from every other node in the network. And this might take another round to do that, right? So now we have this state proof of the entire network or in the entire file system through this Merkle tree. And this right here is what is called the state proof. Now if we compress this even more, I've got this little record here that includes the file that is a record of my transaction plus a bunch of signatures and some hashes, and this is my state proof. And every node is going to go around and do the exact same thing until everybody has that state proof. And everybody's going to do it kind of at their own pace, and some of them are going to be faster than others. But what I can do now is I can go back to the node, and I can say, hey, node, give me my record. So I do a transaction called get record. And that node's going to hand me back that record with the state proof. Now, this is a portable version of trust. And if we think about it, a state proof is the network's perspective of consensus, right? So a receipt is a single node's perspective of consensus. And if you need to be fast, you can just say, give me a receipt of my transaction. Here's my transaction ID. Tell me that it's reached consensus. Yes. I'm going to go to somebody else and ask the same question. And if you need it fast, you can do a receipt approach and build a certain amount of trust in option 1. But again, that's the node's perspective, and that requires you to make multiple transactions. And only you can see that. Whoever's making the request is the only one that can validate that. And it has to happen quickly because those receipts don't last very long. They live in memory, and they go away after a period. Records, on the other hand, stay on the file system for a longer period of time. And not only can you tell people to go pull their own record, their own copy of your record, but it's also portable now. You now have a file in your hand that includes the original transaction plus a state proof, and you can hand that to anybody. So imagine being at the Department of Motor Vehicle, you pay your traffic fee or your license fee or your registration fee, and 10 years later the DMV comes back and says, you didn't pay your fee. You're like, well, wait a second. I've got a state proof right here that says that my account ID was debited and yours was credited, and I've got an entire network witnessing this, and here's the state proof of all these signatures proving that I did in fact, or my account did in fact pay your account of the amount that was required for this. So this is pretty powerful. This is a portable thing, and this is very valuable if you need to prove to a third party that the state of your transaction, that something is true or that consensus was reached. This is very important. It's also much slower because there's lots of cycles in here. There's a signing cycle. There's a collection of signatures cycle. There is writing to the file system, so there's I/O. This is a slower mechanism. But if you need this level of trust, you can do that. Now there's a third option. And this is what I call go ask yourself. And this kind of requires us to talk about something new. Shouldn't say too new. Lehman talked about it earlier. He talked about it this morning. But it is a new concept for this conference. And this is something called the mirror network. Does everybody remember the mirror network that Lehman talked about? I'm going to show you a graph right now, or a picture of what this looks like. So we have Hedera nodes in the middle. These are the nodes that are responsible for collecting transactions, bundling those transactions into events, gossiping, building a hash graph, creating records and signing those records, and building state proofs. That's what these nodes are about. It's about generating the consensus and signing it, securing that consensus or making that consensus safe. That's their responsibility. The mirror nodes, the circles with the M's on them, they can do everything the Hedera node can do, except they cannot create events. In other words, they cannot affect the structure of the hash graph. So they do not contribute to what reaches consensus. They don't changed the structure of how we calculate consensus. So what this means is they become almost like a read version. It's almost like a fast read of the hash graph. And what happens is the Hedera nodes all build these events and gossip them around, and then nodes will periodically gossip out to a mirror node whatever it knows, and then those mirror nodes will gossip amongst each other until they've all built the same hash graph. Who can host mirror nodes? Anyone. As a matter of fact, the bigger this network gets, the more trustworthy it becomes, because big networks are more trustworthy. They're harder to beat. And these networks can do a lot of things on their own. If you built your own node, assuming it meets the performance requirements of the network, if you build your own node, you can listen to everything that comes through on the network, and you can verify every transaction that comes through by its position in an event that exists inside of a hash graph. So if you're a dApp developer, or you're an enterprise, or you're a service provider, or you're a telco, and you're like, I want to send a transaction into the network, and I don't want to trust the network or take the time to go check the network or pay the extra fees to generate a record, I'm just going to host a mirror node. And when I send that transaction into the network, that one's going to go through and get consensus, and eventually one of the Hedera nodes will gossip with a mirror node. And if you're hosting a mirror node, your mirror node will now learn that information, and then through however mechanism you want, if you want to filter out the entire hash graph except for things that apply to your account IDs, or if you want to archive things and sell it to people, or if you want to run complex business logic on the information that's running through, analytics, whatever you want, you can do that on your own mirror node without affecting the performance of the main Hedera network. And because this is a gossip protocol, and it is read-only, I shouldn't say it's read-only, because it's a gossip protocol and these nodes are not creating events, as it grows, it'll get a little bit slower, but it'll be exponentially fast. So where 1 million nodes may not be a whole lot slower than 100 nodes. Maybe if we had to wait 30 seconds for my mirror node to become aware of a transaction, that might be acceptable if I don't have to pay for a record. So there's some trade-offs here. If I need something in a really quick period of time, maybe I do receipts. Option 1, do receipts and then verify the receipts. If I need something that's portable and trustworthy, then maybe I can go ask for a record, and that's going to take a little bit longer. And if we've got millions of nodes in the mirror network, and it might take a little bit longer for my mirror node to become aware of it, but now I have the ability to build my own records and my own state proofs. I actually have the hash graph, so I can verify everything in the hash graph as far as signatures go. Every event in the hash graph is signed against the previous 2 events. So you've got the same security model that you have, that even the Hedera nodes have. So now you have options, whatever you think is important. So think about this real quick from a micropayment perspective. So assume we've got a million nodes in the network, and I don't know what the number is. I'm sure Lehman has a much better explanation of what the number is, but we'll say it takes 20 seconds for my mirror node to become aware of transactions that enter the network that relate to my account ID. And these are just cryptocurrency transactions. And I own a coffee shop, and I have a little kiosk, and somebody comes up and scans their Hedera wallet, and they pay a transaction into the Hedera network, and then I've got a node back at headquarters that's just listening for transactions that comes across, and it goes, oh, this one applies to this transaction over here in this location, and now you've got your coffee within 10 seconds using cryptocurrency, or 20 seconds with cryptocurrency on a big network. On a smaller network, it's going to be a lot faster. But still, if that's okay, if it's okay to wait 30 seconds for a transaction, if it's okay to wait 20 seconds, if it's okay to wait 10 seconds, and you're more interested about getting the information and not relying on a third party to generate records for you or wait or pay for those records, then this might work for you. If you need to do micropayment transactions, so this is where it gets really interesting. So let's think about a paywall. I'm going to talk about some use cases here, but let's think about a paywall real quick. If I host a website, maybe I also have a mirror node. Maybe I'm a big news organization. I've got a mirror node, and on my website, you can pay per page view 0.01 cents every time you view my page. I don't want to generate a record because that would make it infeasible or impractical from a pricing perspective, potentially. I don't know what records are going to cost yet. We're still working that out. But it might not be the price point that I want. So what I do is I pass in a really, really, really cheap cryptocurrency transaction into the network, and the fee on that is super small and almost not noticeable compared to the 0.01 cents I'm charging to see this page. And then I just listen for the transaction to clear. And maybe I'm okay. If the pre-check comes back as okay, I'm okay showing them the page until I get that confirmation. And then when I get that confirmation through my mirror node, I either continue to let them to read or I shut it off. If I continue to let them to read, that means that I got a confirmation of the transaction through my mirror node. So now we can do things really fast. And if I'm okay with pre-checks happen in milliseconds. So somebody pays, and the page could just pop on because the pre-check came back immediately. And then in 10 seconds, the page turns off if you actually didn't have the right balance. Or maybe it just stays up, because in most cases, pre-checks are going to be okay for smaller transactions like that. So this is the power of mirror nodes. Title of this talk is the power of the memo field, and we haven't talked about that at all. So let's take a quick look at a transaction. A transaction consists of a transaction ID, which is your account ID plus a timestamp. Includes a transaction fee, a node ID of who you're going to pay to process this, the valid duration, your record Boolean. This is the one that says whether or not to create a record. But if you leave this as false and you have a mirror node, you're good to go. You've got a memo field, and you've got a body, depending on the type of transaction you've got here. Let's talk specifically about the memo field. I haven't talked about this yet. This is the title of my talk, and we're just getting to memo fields. I want you to understand this. We got 100 bytes to play with in this memo field. What can you do with 100 bytes? I'd argue you can do a whole lot of stuff with 100 bytes. You can do a SHA-384 hash. If you wanted to hash something and just get a timestamp on it through a transaction, a trusted timestamp. Just so you can say, I generated this file, I put the hash of the file into the memo field, submitted an almost zero cryptocurrency transaction, a zero H-bar cryptocurrency transaction. My mirror node watches it, comes back, and I can now see, all right, I now have a proof. I can generate my own state proof even from that, or if I want to keep the whole structure, that yes, this has reached consensus, has been signed and witnessed by all of these other nodes, and this hash now has a fair timestamp on it, and I can say, I know this file was created at least before this timestamp, because I can take this file, hash it, compare it to the hash that's in this transaction, and I have a fair timestamp on that. So when you're talking about tax filings or SEC filings or anything like that, they have to be filed by this date. Well, now I can prove it. What about maybe just a small text message? Maybe you've got a messenger. Maybe you've got invoice numbers you want to put on stuff. You've got other things that you don't mind being in the open and in the clear. You can put 100 bytes of data. That's a lot of characters. It's 100 characters. You can put small encrypted messages. So if you are going to use encryption, you don't want anybody to see it, small encrypted messages can go on here. You've only got 100 bytes. Encryption gets a little tricky with 100 bytes. But that's a lot of things you can do there. And when we think about some of these use cases, we can get a little creative. We've got micropayments, which is the one I just talked about. If you've got a paywall, for example, and you host a mirror node, you don't need to pay for a record every time you process a payment on people watching your videos or reading your articles. You can collect micropayments quickly. And if you're hosting a mirror node, you can be assured that you got paid because you're watching the Hashgraph on your node. What about supply chain? Supply chain is really a big business process with multiple actors, and there's a bunch of these handoff points, right? These interaction points between these actors in this business process. Well, what if you don't have to track the entire process in smart contracts, but you document the handoffs or the interactions with offline documents that get hashed, signed by both parties, dumped into a transaction, and then thrown into the network. And then if you've got a mirror node, every party that has a mirror node now has confirmation and witness of that handoff. So now we got to think a little bit outside the box. Let's not try to shove everything into a smart contract. Smart contracts are good for some things, but for very complicated applications, they get very expensive and heavy and slow. I think we can do trust a lot better for supply chain management. Telecom is another place. We can do it there because things like roaming reconciliation, we can do discovery and reporting of roaming subscribers on a roaming network versus a home network. And they can even reconcile against each other in the same back and forth conversation using transactions. So here's just a few things that I've thought about. There's a whole list of tools you have in Hedera, and we have just looked at the Memo field plus a mirror node in the entire API. There's lots of tools out there, and there's lots of things you can do. But if we're talking about trust, this is what we're trying to generate. We might need to get a little bit creative, but I believe we can generate trust. In this case, I'm showing 3 options, but there's lots of ways we can generate trust using the Hedera platform. The real question is, what future will you build? Thank you very much.